Then, this is what consumes him. The three classical Greek problems. He knows at this point in his life, he's making a major contribution to pretty much anything that exists. That has to do with nature, the painting, the art. He knows it. He doesn't need the worship of Michelangelo, Raphael, or the popes to tell him this. He just knows it. So he says, I'm going to do something really important, math, right? That's what Jolie says math is important. There's just three big Greek problems that nobody can solve. I'm going to give it a shot. Wow, this is a big, big thing. The rules of the game were that you were only allowed to use ruler and compass, because those are the rules. Right? So you've all seen ruler and compass constructions in high school. Right? You take a compass and a ruler, and then you make these measurements, and you make an equilateral triangle with it. So the first big problem was to trisect an arbitrary angle, which was proved to be impossible about 150 years ago, 500 years ago. I mean, even some kids now write to me and say, you know, I've trisected an angle. See, you got to remember what these things are, right? These are problems that are known to be impossible to do. So don't try it at home, because no matter what you do, it's going to fail, because we proved that it's impossible to do it. So you can only approximate solutions, which is okay. But back then, it wasn't known to be impossible. To find a square equal in area to that of a given circle, so a circle in a certain area, you want to be able to construct through ruler and compass a square with the same area as a circle. And then to find a cube whose volume is twice the volume of a given cube. And here's the sketches of his compasses. He spent a lot of time on the last two. He didn't even dare trisect an angle. I'm not sure why he didn't try out. We don't have, well, perhaps in the other 80% of the manuscripts that are missing, there might be something in there, but we don't know. So using ruler and compass only, the ruler can only be used to join two existing points by a line, and the compass is used to make arcs. Those are the rules. So here's a circle with a given area. We'll assume its radius is 1, its area is pi, right? Pi r squared, to the Greeks. Find the square with area equal to pi. In other words, construct it using ruler and compass so that its area equals pi. So problem 2. Start with a circle of a given area. So we have here, so if you want to find the square with area equal to pi, then each side has to be equal to pi, which means that you're able to construct this number. So can you do that? The problem is that now we know that root pi is not a constructible number. We spent about 20 years trying to do this. But we did do some really interesting stuff. Now look at this diagram that comes from Codex Atlanticus, a very important codex. And this particular part right here that I'm emphasizing. So here's a right angle triangle. There's a certain area. And these he calls looms, because they look like, sections of a loom. Leonardo proves that the area of this loom plus the area of this loom equals the area of the triangle. And actually, I can give you a proof in about 3 minutes with Word, using the Leonardo technique, which uses only Pythagoras' theorem and the fact that you know the area of a circle. This is a really interesting result. Why? Because this gap between the two looms is what makes it impossible, in fact, to square the circle. If you made this triangle here an isosceles right angle triangle, then this one would be equal in area to this one. And if you expanded this triangle, this gap would get smaller and smaller and smaller. And if this triangle had been a mile or a kilometer on each side, that gap would be so small as to be invisible. And if that construction terminated, i.e. there was no gap, you would have actually squared the circle. Why? Because this would be a semicircle, that would be a semicircle. The sum of their areas equals the area of this, half the area, actually, like this triangle. So you get it. But he didn't see that. He didn't see that the impossibility could have been gathered, at least from here, in this picture. But he claimed success on the night of St. Andrew, 3rd of November, 1504, 15 years before he died. I reached the end of squaring the circle. I got it figured out finally, right, after all these years. And at the end of the light of the candle, of the night, and of the paper in which I was writing, it was completed. So he was convinced he figured it out. That's it, Madrid Codex. Marginal law, Madrid Codex. And duplicating the cube is also an interesting way. I should tell you something about the Madrid Codex later if you ask me. We'll leave it for the question period. Given a cube, to find another cube whose volume is double the first. So again, we have to construct various numbers. So this is volume 1. You want to be able to construct a cube whose volume is 2. So this means you have to construct a certain number. So, let's see. Double first. So let's go over here. Yeah, so here I'm showing you, in fact, how you actually build these numbers. So when you're actually constructing a square using ruler and compass, you see what you're doing is you're actually constructing a right angle, which is how you do it with a compass. And then you join this, and then you join that, and then you use your compass to make this section right here. And so you have that, you make another right angle here, you make another right angle here, so you built yourself a square using ruler and compass. And the new square now must have area equal to 2, so which means you have to be able to construct the square root of 2. And that is doable, right? So you need to find root 2 using moving ruler and compass. And if you take the diagonal of the square that I just constructed and use Pythagoras, which was known to Leonardo, you've constructed the square root of 2. Okay? That's 1, 1, root 2. So you constructed that number, which happens to be an irrational number, but you constructed it nevertheless using ruler and compass. So root 2 is constructible, and we can find, sorry, and we can find the, we can actually duplicate, in that sense, the square. Now, to duplicating the cube, that if the side has length x and the height is x because it's a cube, then its volume is x cubed. The x cube has to be double the volume of the first cube, which assumes that volume 1. So you're trying to construct a cube root of 2, which is 1.25992. So problem 3 is like the problem constructing the cube root of 2, which is constructing the edge of this cube. But this number is not constructed. That was proved about 150 years ago. Galileo and people like this. So problem 3 is also not solvable. But look, here's one of his Codex Arundel, folio 283. Here he's taking a 3-dimensional triangle and he's putting these cubes on the side. He's trying to verify Pythagoras in R3. Interesting. I mean, the guy is thinking about everything. And then later on, he tries again over here. I mean, he's trying to get these really interesting, and then there's all these multiplications around and additions. So he's using this for scrap paper. So all his observations are going to these folios, the scrap paper and this important stuff, and then scrap paper as well. This is a fountain he designed, another fountain, and it goes on and on. There's all these ideas on the same page, right? But this is interesting, his version of Pythagoras. And here it's clear, he's writing, you see he's writing mirror image 27, that's 27 mirror image, right? But here, look, you can actually see 28 written the right way. So why is he changing his mind when he's writing numbers? Interesting. Probably because he was taught to multiply using the numbers in the right way. And if he had to multiply the other way, he'd have to sort of reset his mind, reboot kind of, right? And say, so here we have some other designs here in Arundel. We have various perspective drawings and cubes in certain positions. Here he's trying to duplicate the cube. See, so he puts a cube inside and then he doubles the sides, and he's hoping that this might work, but that doesn't work either. Here's another one, a little cube inside another cube. And so here is his theories in duplicating the cube. Here's perspective drawings of cubes in a line, vanishing point. And here you have Codex Atlanticus. He actually realizes that he's not going to be able to do it because his time is running out, probably. And he approximates the cube root of 2 by 5 folds, which is 1.25. The true value is 1.25992, like 1.26. That's pretty close for an approximation for a cube root of 2.